All right, we'll start with questions, because I know there's questions on the homework. Which ones? 17. X cosecant x? Okay. All right, so we have limit x is approaching 2 pi from the left, because there's a little negative sign there, of x cosecant x. So what might help here is to realize, first of all, that cosecant is 1 over sine. So if you rewrite this, you can write limit x approaches 2 pi from the left of x over sine x. Do you agree? Because cosecant of x is 1 over sine x. And so you can really just look at it as being x over sine x. And now what happens is x goes to 2 pi. So on the top, where are we headed? To 2 pi. On the bottom, where are we headed? Sine of 2 pi, right? Sine of 2 pi should be 0, which is bad. So we get 2 pi on top, we get 0 on the bottom, right? However, this is a fixed number. In fact, it's a fixed positive or negative number? Positive, because 2 pi is positive, right? So it's a fixed positive number over 0. And anytime we have a fixed number over 0, we have how many possible answers? 3. What are they? What could it be? Infinity, negative infinity, or it could be that the limit does not exist. Those are the only 3 outcomes, all right? Those are the only 3 things that can happen now. So I know the top's positive. I just need to figure out if the bottom is approaching 0 through positive or negative numbers. That's all I have to figure out. So the way I'm going to figure it out is I'm going to look at what the denominator is. It's the sine function, right? And I would like to figure out what's happening to sine of x as x approaches, here's my number line, I'm approaching 2 pi from which side? The left side. Which means my numbers are a little bit smaller than 2 pi, right? Now, before in class, what we did is we just picked numbers, didn't we? And just plugged those in. But when we did it in class, we were just plugging the value of x was just getting plugged in here. It's very easy for us to tell what the answer was, because it was just plugging x in. Here, we're plugging x into a sine function. So it would be better for us to also look at the sine function and what's happening to it as we get close to pi over 2 from the left. So next to this, I'm going to graph sine. Here's 2 pi out here. Sine does this, doesn't it? It goes up, comes down, comes back up like this. That's your standard sine curve. And I'm trying to approach 2 pi, right? From the left side, so shouldn't I be on the curve right here? And I'm coming in, I'm approaching 2 pi. We already know we're approaching 0, right? That is getting closer and closer to 0. But we're coming up from below the x-axis, which means that those values are very, very small negative numbers. So I know that I'm approaching 0 here through negative numbers. Y'all see that? And since I have a positive over a negative, that means my ratio would be negative. So your answer is negative infinity. Does that help? Yes.
I got the same answer, but I did it completely backwards.
Okay.
I drew the
Cosecant?
Yeah, I drew cosecant.
That's okay.
And then I plugged in the 1.9 where the 1.9
Okay.
and just did like the number line thing.
That's okay. That's okay. No, that'd be okay. So you just did more of like a table approach? Okay. Well, then let me retract my statement. I don't mind you plugging in values close to here, but I still need to see that you got fixed over 0. Like, that's the most important thing to me right here, this piece right here, is the fact that you realize that there's 3 possible answers. If I wanted you to do the table approach, you know, we would do the table approach all the time, and that can be very tedious and time consuming. Plus, if something goes to infinity, you can't make a table if something's going to infinity. You can let x get bigger, but that's, you know, what's big enough? When you're dealing with infinity, there is no big enough. So if you identify this at least for me and then do table, I'd be okay with that, but I'd prefer something more along this line. Other questions? I'll talk review. Don't worry, not yet though. Can we wait on review? Yes? 21? All right. Limit t goes to infinity. Root t plus t squared over 2t minus t squared. Well, what's happening up top? This is infinity plus infinity, right? So the top's headed to infinity. What about the bottom? It's infinity minus infinity. What's infinity minus infinity? I don't know. I don't know what it is, okay? However, I could factor this, couldn't I? Look at the bottom real quick. I'll just write it down below here. I could factor out a t, couldn't I? Be left with 2 minus t. Now let t go to infinity, and what would happen? You would have infinity right here, right? Infinity right there. Times what? Times 2 minus infinity. 2 minus infinity is negative infinity. So that would be negative infinity. What is infinity times negative infinity? Negative infinity. So you basically have infinity over negative infinity. And infinity over negative infinity is negative 1? No. Right? That's why we're here, right? Because that's not negative 1. That's something we don't know. So I first need to realize it's something I don't know. And this is the stuff on the test. I want to see these things because this gets you credit. Remember, I'm not giving you a multiple choice test. So the more you show me that you understand what you're doing, the concepts behind this, the more credit you get. You just leave it blank and you don't get any credit. All right, so I know this is a bad situation. The only thing I really have is some algebra or some trick. What did we do in the past when we had something like this? We did conjugate before. Yes, we did do conjugate. I'm not going to say we didn't. But infinity over infinity, first time I ever showed it to you, we tried to divide the top and bottom by something that would kill off the highest power in the bottom. So we could go 1 over t squared top and bottom and try it and see what happens. Right? We could try that. So how about limit? So if you were to come in with conjugate, I don't know what would happen. I'd have to see, but I would imagine that might actually be just an exercise that you would regret doing later. But, you know, at least you tried something, right? So I'm going to distribute. I'm going to leave this back to its original form like that. All right, now we get to play with exponents. When I distribute this through 1 over t squared and I distribute it to root t is the same as t to the 1/2, right? So we have t to the 1/2 over t to the 2nd power. What's that going to leave me with? 1 over t to the 3/2. Very good. So you get 1 over t to the 3/2. Then you distribute, that's here to here. Now go here to here. What do you get? Plus 1 over, now here to here. It's 1 over t squared times 2 over 2t. 2 over t minus 1. Questions? Now let t go to infinity. What happens? This right here vanishes out to 0, okay? It approaches 0, so that's getting smaller, 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 because we have what? Fixed over infinity? How about this one? 0 again. It's going to vanish. It's going to go to 0. And then all that's left is what? 1 over -1, so the answer is -1. So it actually turned out that that was a -1. For this particular problem, it's -1. But in general, infinity over negative infinity is not -1. That reminds me, I don't know why I just thought of this. Little FYI here. The difference between this, I see this a lot in calculus classes. The difference between these two. Just in case you write your zeros like this, let me tell you a little bit about this. This is not the number 0. I know in military, I believe they do that. Anyone in military, they use that for 0? Okay, in mathematics, 0 is the number 0, right? If you list out like on a number line, 0, that's this, okay? This in mathematics means the empty set, which means the set that contains nothing inside of it. So like if I write down a set of numbers, 1, 2, 3, that set has 3 things in it, right? 1, 2, and 3. This set has how many things in it? 1 thing. What's in it? The number 0. What's the set that has nothing inside of it? That's the empty set. Okay, this right here means the set of nothing, where 0 is just a number in the real numbers. Totally different concepts in mathematics. So, just a little FYI. Next question. Again, off homework for now. Come on. You said you did like 2, and So everyone got all of them. The rest of them. Where? On 20. All right. On 20, x goes to infinity. 1 minus x squared over x cubed minus x plus 1. All right, where's it headed? X is going to infinity. Where's the numerator headed? Negative infinity, right? Because you're taking 1, you're subtracting infinity squared. So that's negative infinity. Over, how about the bottom? Infinity minus infinity plus 1. What's this infinity minus infinity? Well, we could look at that as being infinity times x squared minus 1 and then plus 1, right? So again, what I did is I just factored an x out of these two and left me with this. What would infinity times, what's this? Infinity squared minus 1 is still infinity. So you get infinity times infinity, which would be infinity plus 1. Still infinite, right? At the end of the day, it's infinity over infinity, so can't do anything about it. You have to do some algebra. How would we attack this one? Divide everything by highest power of x that you see in the denominator, x cubed. We're going to come in with x cubed. Limit x goes to, if you did x squared, it's going to work for this problem, but it's kind of dangerous because it may not work for others. 1 over x cubed, 1 over x cubed. We're going to distribute that through the top. We're going to distribute that through the bottom. This will give us limit. And yes, I'm still writing the limit because I haven't let x go to infinity yet. All right, distribute through the top. What do you got? 1 over x cubed minus 1 over x over 1 minus 1 over x squared plus 1 over x cubed. And now let x become infinite. And lots of stuff go away, right? This right here goes away. This goes away. This goes away. This goes away. That's what made me think of empty set a second ago. This is not the empty set. I'm just saying they vanish to 0, right? So what's left on top? 0. What's on the bottom? 1. But 0 divided by 1 is 0. Okay, that's okay to have. We cannot have 1 over 0. If it's 1 over 0, there's 3 possibilities, right? Infinity, negative infinity does not exist. But if it's the other way around, it's just 0. So we're done. The answer is 0. So this is good that you asked this question because, look, in the previous problem I did, we had negative infinity over infinity, and it was negative 1, wasn't it, the limit? But here we had negative infinity over infinity, and we actually got 0. All right, what else? No? All right, well, so no other questions. I wanted to just finish up some of the formal notes from last time. Anytime you take a limit of a function as x goes to infinity or negative infinity, and I'll let you all know right now, I have avoided going to negative infinity in this class. I'm not going to test you on that, okay? But it's just basically plugging values into the function that get really big, but they're big and negative. All right, so it changes things up a little bit. But in either case, if that limit approaches a number, like we got negative 1 a second ago, right? And then in this problem just a second, right? The one we just did was 0. The one before that was negative 1, right? Both those answers, in both of those problems, we had answers. That L is our answer. Then what we would say is that that's a horizontal line. Our graph is going towards negative 1 or going towards 0. That creates what we called in college algebra a horizontal asymptote. Don't remember that from college algebra? Okay. So that's just the definition, all right? This we already saw, limits at infinity. We spent a lot of time on that last class. This problem right here, what's the limit as x goes to infinity of sine x over x? Why is it 0? Do y'all remember that from last class? Why this one is 0? What's happening on the top? Sine x, what does sine do as you go to infinity? It goes up and down, right? What's going on the bottom? The top's not fixed. I use a different term for it, though. Bounded, right? We said the top was bounded, and the bottom was approaching infinity. Anytime you have bounded over infinity, it goes to 0. So we did talk about that last class. And this is a summary, all right? Anytime you take a limit, all right? Anytime you take a limit and you get the following, one of these 7 things, then here's what you do. Anytime your numerator and denominator both go to 0, you have to do some algebra, right, or some trick. Anytime you get infinity over infinity, and it doesn't matter if it's positive or negative on top or bottom, it does not matter, you have to do some algebra. Anytime your numerator is constant or fixed, divided by your denominator, which is 0, you get infinity or negative infinity, and I forgot to put in here what else? Or does not exist, all right? What if your numerator goes to 0 and your bottom does not go to 0? You get 1, or sorry, like we just had 0 over 1, that was just 0. What happens if you have a numerator that's constant or fixed and your denominator goes to infinity? That goes to 0. What if your numerator gets huge and your denominator doesn't move? Then it just gets big, right? Either positive or negative, but it gets big. And then this is the one we just talked about. If your numerator is bounded and your denominator goes to infinity, the answer is 0. Those are things we should just kind of have hardwired as we move on. Yes, they are. These two are very similar, except that we're replacing constant with the idea of bounded. All right. Now, this is the last thing we're going to talk about, continuity. The idea of continuity, since I would hope everyone watched the video, was that if you can draw a function without picking up the pencil, right? If you can draw without picking up your pencil, it's continuous. That's the basic idea of continuity. Would this be continuous or not? No, but it's continuous over here, isn't it? It's just not continuous when I get there because there's a hole. So I have to pick up my pencil and then continue drawing it. So at 2, I would be discontinuous at 2. At x is 2, I have a discontinuity. This one is still discontinuous at 2 because I draw it. When I get to this, I have to pick up my pencil, I have to fill in this hole, and then I have to come back and go like this. So that is discontinuous at 2. This one is continuous. It's actually continuous everywhere, and when I get to 2, I don't need to pick up my pencil. I just keep going through, right? So continuous, you draw without picking up your pencil. If you have a discontinuity at a point, and we say it's discontinuous there. There's 3 basic types of discontinuities. Jump discontinuities, infinite discontinuities, and removable ones. Here's an example of a jump discontinuity. I draw it, everything's great, and then at some point I go, oh, I got to get down here, right? So I have to pick up my pencil and then go. So do you see why they call it a jump? It's like a jump in the graph. You got to go here and then jump and then go, right? Anytime we have a jump in the graph, it's discontinuous where that break occurs. Infinite discontinuity, vertical asymptotes. No matter what, when I draw a vertical asymptote, I'm eventually going to have to pick up my pencil and go to the other side of the asymptote. So that's going to be a break in my graph, so I'll have a discontinuity there, all right? And then the last one is removable. Anytime we have a hole in the graph, we have to pick up our pencil, go over the hole, and then keep going, right? They call it removable because there's an easy way for you to remove it and not make it a bad situation anymore. How could I fix this one? How could I make this continuous there? Just put a dot there, right? If I just define the function there, that's pretty simple to do, right? Define the function, and I'd be okay. So I can remove that discontinuity pretty easily. This discontinuity I can't remove unless I change the whole shape of the graph, right? I can't make the 2 meet up there because they go to infinity. This one, I can't really remove that because it's a big jump. What am I going to do between here and here? Connect it somehow? I can't connect it with the straight line or it'll fail the vertical line test. So there's a lot of issues there. I'm just trying to get you to see why we call it removable. It's just because it's easy to fix that if we needed to. Now, then I talked about continuity from the left and from the right. So this right here, if I look at this function, it's discontinuous at 2, right? Discontinuous at 2, because we have what kind of discontinuity there? A jump, right? However, if I just look at the whether or not it's continuous from the left at 2, I go to 2, I look to the left of it, is it continuous? Yes, because I come up all the way to that point and I have the function is defined there, so I stop drawing and it's over, right? I come in from the left, I stop. This one would be continuous from the right at 2 because I come in to the right, I draw it, and then when I get there, I have a stopping point, right? I actually stop, and I'm done. Now, would this one be continuous from the right? No, why not? Because there's a hole. That's the big thing. So I draw it from the right. When I get there, like, I don't have a stopping point, right? Like, how close can I get to that hole? As close as I want, right? So if you ever say, look, I'm done, I can always go half the distance again, couldn't I? Like, there's always some more I can go. Yeah, there's no number closest to 2. Do y'all agree with that? It's like if I said, look, I'm trying to get to that wall, I can go halfway, and then I can walk halfway again, and I can go halfway again, and then halfway again. Is there some closest point to the wall? I always can go half of that distance, right? Whatever distance is left, I can always go half. And I always take that and divide it by 2 and be half, and then half and half and half. So there is no closest point, so I can never stop with my pencil. Does that make any sense? Like you wouldn't know where to stop your pencil at all. This one would not be continuous from the left, right? Correct? All right, a function f is said to be continuous on an interval if it's continuous at every point inside the interval, and then at the endpoints it only needs to be either left or right continuous. So look at this interval, this function between 1 and 3. It's continuous on the entire interval. You draw without picking up your pencil. When you get to the left endpoint, you are right continuous. When you get to the right endpoint, you are left continuous. So therefore, it's continuous on the whole interval. Does that make sense? All right, this is just some properties of functions that are continuous. If you have two continuous functions and you add them together, it's still continuous. Multiply by a constant, still continuous. If you multiply two functions that are continuous, your result is continuous. If you divide two functions that are continuous, it's continuous, so long as one of them is not 0. And then this is the big theorem right here. This is the part that's most important to us. Every polynomial function is continuous everywhere, negative infinity to infinity. So think back to a parabola, right? You could draw a parabola, never pick up your pencil. Think about a cubic function. You know, these things from college algebra. All those functions, you could draw them without picking up your pencil. Rational functions were the ones that had, so here's polynomial, right? Nice, draw it without picking up my pencil. Rational functions, they had these breaks in them. They had asymptotes, right? So this can't be continuous everywhere, can it? No. But it's continuous on its implied domain. That means everywhere the function is defined, so if you take out the vertical asymptotes, everywhere else, it's nice. This is nice and smooth. This is, you can draw that piece without picking up your pencil. You can draw this piece by itself. You can draw that piece. So separately, each piece is continuous. All trig functions are continuous on their implied domains also. Sine function, cosine, tangent. Exponential functions and log functions are all continuous functions, right, on their implied domains. Here's one of the major results of continuous functions. And this is kind of weird. If you watch my video, I hope this made sense, but I'm going to actually do a problem just to work it out, because you can really overcomplicate this. I don't want you all to do that. Use the intermediate value theorem to show that this equation has a solution inside the interval 0, 1. All right, so here's what we do when we try and solve an equation. We move everything over to one side. So if I'm trying to show that this equation has a solution in the interval, what was the interval? 0, 1? What I'm trying to do is convince you and whoever else that there is some value of x I can plug in that would make this equation true. I just have to convince you that a solution exists. Like, for example, is there a solution to this equation? Only if you have imaginary numbers, right? If you're not allowed to have imaginary numbers, there is no solution, right? Okay, so there are some equations that don't have solutions. I want us to show that this one does. Here's another example of an equation that doesn't have a solution. Sine x is 2. Right? Sine is bounded between 1 and negative 1. Can never be 2. So that has no solution. What we're trying to do is show that this equation does have a solution and that it does exist between, the solution is somewhere between 0 and 1. Notice the problem does not ask for you to actually find it. It just asks for you to show it exists. So the way we do it is we move everything on the equation to one side. and we call the left side of this equation f of x. So it's like a function. And if you ever set a function equal to 0, what does that represent graphically? If I say set a function equal to 0 and solve, what does that give you on the graph? Other way. X-intercepts, right? I don't know if you remember, whenever you're trying to find like the x-intercepts of a parabola or a polynomial, we said set the function equal to 0. Well, what I've done is I've moved this over, so I've created something that looks like a function is set equal to 0, right? Yes? Now, I don't know what the graph of this function looks like. I don't know what it looks like, but I'm going to look at its value at 0 and at 1. So tell me what f of 0 is. What is this function's value at 0? Well, that's cosine of 0 minus 0. Cosine of 0 is 1, right? So you get 1 minus 0 is 1. So that means that at 0, I'm up here at 1, correct? Now plug in 1 into this function, the other endpoint of the interval. What's f of 1? Cosine of 1 minus 1. And to figure out what this value is, cosine of 1, what would you do? You could use a calculator, make sure you're in radian mode, and then subtract 1. What you're going to get if you do this on your calculator is a negative number. Right? It's going to be a negative number. So that means that out here at 1, I'm some negative number. I'm going to put a dot. Why is it that I know that between 0 and 1, this equation has a solution? Because this graph, right, this one I'm trying to draw in blue, has to go from this point to this point, right? And not only that, this function f, these are both continuous functions. Isn't the cosine function continuous? You draw it without picking up your pencil. And then I'm subtracting x. X is a polynomial, which is continuous also. We just said in previous notes, you take two continuous functions and subtract them, you still have a continuous function. So I know that this function is continuous, which means I must be able to draw it from here to here without picking up my pencil, which there's absolutely no way I can get from that point in the top left to the top right without crossing the x-axis, right? There's no way I can do it. I don't know where it's going to happen, but somewhere in there I'm going to cross through, right? Somewhere. And that's enough to show that the solution exists. I don't know what it is, but it's somewhere between 0 and 1, right? So really what you're looking for is a change in signs, aren't you? From positive to negative, or it could have gone negative to positive and that would have shown me the same thing, right? So the heart of a problem like this is to move everything to one side and then look at that as your function and evaluate it at the two endpoints. If these two things differ in sign, then you can guarantee me that the solution exists somewhere inside there. Does that make sense? You're okay with that? Now this leads us to a more profound question, which is, on my calculator, or better yet, if I go to Wolfram Alpha, which we like going to, and I say solve cosine x equals x, it gives me an answer of 0.739085, right? It's solved that for me. Now I'll come back to that, all right? This is what we were trying to solve, right? There is no way to solve this by hand, all right? I don't care what type of math person you are, how good you are at math. I can't solve that by hand either. I mean, it just cannot be done. There's no algebraic move I can make to solve for x. You know, some people might say, all right, we'll just come in with arc cosine on both sides. You know, you learned about these inverse cosine or inverse trig functions. If you do that, won't you free up this x out of the cosine? Won't you release it from there, coming in with its inverse, so you get x on the left side? But what have you done on the right side? You've trapped the cosine on the right side, or you've trapped the x in a cosine on the right side. So there's no way to get x by itself on one side of this equation, just not possible. So I can't solve for it by hand. So why is the intermediate value theorem useful? What's the point? Why do we show it to you in calculus? Because Wolfram Alpha used the intermediate value theorem to actually find this answer. And here's how it did it. Okay, your calculator doesn't know how to solve this. Your calculator's not smart. All your calculator knows is what? All a computer knows is what? What is the only thing a computer understands? Where are my computer science people here? The basic idea of a computer. Most primitive thing about a computer. Zeros and ones. Which if you go even more primitive than that, it's either yes or no. It's electrical signal is there or it is not present. That's all a computer can do. All right? That's it. So here's how the computer works. You tell it to do this, right? And so what it does is just what we did. We move it to one side like this. And then it starts plugging numbers in. See, one advantage computer has over us is it can do things fast. It can do addition, subtraction, multiplication, division at mind-boggling rates, like millions and millions of computations in split seconds, which for us we can't do, right? So what the calculator does is, okay, it starts off, maybe it plugs in negative 1 million or something like that, and then it plugs in 1 million. There's some numbers that are pre-programmed into the calculator, and it says, let me try those two values. And when it plugs it in here and plugs it in here, it looks to see what the signs are. And it looks for a change in sign. So maybe here it was positive and here it was negative. So it knows that if you graphed it, here at negative 1 million, you would be up here, and then over here at 1 million, you'd be down here. Got it? So it knows that it crosses through somewhere, doesn't it, the calculator? So it uses what's called now the bisection method. It now cuts that interval in half. So it cuts it here and just looks on each of these windows. So look between negative 1 million and 0. Is there a change in sign? It's positive, and over here it would be what? Positive again? So your calculator goes, okay, test it at negative 1 million, positive. Test it at 0, positive. No change in sign, throw that interval away. Then it goes between 0 and 1 million and says, positive to what? Negative. It's somewhere in there. So the computer says, cut that in half. Now, when it checks on this one, what happens? It's negative to negative. No change in sign. Cut that in half. And now it goes in here and it says, change in sign, positive to negative. Do y'all see that? Then it cuts that in half. And then it says, okay, between here and here, no change in sign. Cut that in half. Then it goes in here. There's a change in sign. Cut that in half. Now it's doing that 1 million times before you can even blink your eyes. So what happens is it cuts it down, and the computer actually never gets an answer, an exact number. What it does is it narrows that window down so small that it's within a tolerance that we would find negligible. You know, the distance between the two endpoints is like 0.00000, like maybe it's like 15 zeros. So then what it does is once it finds that interval, it cuts it in half, it takes the average and just gives us the number in the middle. So it's really approximating it, but it's using this idea of cutting in half and using the change in sign the whole time. That's the way a computer does that. Well, I'm lying to you. Computer programmers will realize that this is a very basic method for solving it. Later on, there's more advanced methods for doing it, but it all is based on the same idea that you use the computer's power of evaluating quickly to solve the problem. It's a bunch of arithmetic problems, though. So that's the value, I guess, of the intermediate value theorem. Okay. Is there anything else here? Intermediate value theorem. What am I going to want you to do, just to make sure y'all understand what this is all about? What would I want you to do on a test if I gave you something like this? Just change sign, right, at the two endpoints. So move everything to one side, and then just call that f, and then evaluate the two endpoints, and show me a change in sign right next to it. Change in sign, therefore must pass through 0. Therefore, there is a solution. You're done. Okay? All right, now that's the basic idea of continuity. Let me now refer to the question that I would ask you on a test. I mean, that one we just did is fine, but I'm going to go to the review that I sent out. I hope you checked your email. I did send out the review for the exam. I said to go and look at everything up through number 7, right? But I said you won't be able to do number 5 because we haven't talked about it. So I'm going to do number 5 on this review. It says, find the value of C which makes F continuous on the interval -infinity to infinity. And here's the definition of the function. Okay. C here is what? A constant, some number, right? I'm supposed to figure out what that number is so that this function f is continuous everywhere. Now, what type of function is this when we have actually like a function and we split it up like this? What do we call? Piecewise, right? Piecewise. Is there more here? Oh, I forgot to put here. If x is less than 2, and here if x is greater than or equal to. We call this a piecewise function. Graphically, imagine this line going through x is 2. To the left of 2, what type of function is it? To the left of 2. It's c times x squared plus 3x, right? What type of graph is that? It's a parabola, right? And then to the right of 2, it's also a parabola, right? But the thing is, depending on c, that will change where the parabola is and what it looks like, right? So if I just draw an arbitrary parabola, on the left of 2, it could do something like this. Now watch me draw it first, and then I'll come back. It could do this, right? That would be a parabola. And then it's to the left of 2, so I'm actually just talking about this. Yeah? What's happening at 2 for this one? It's a hole, right? It doesn't exist there, so I would have a hole. And then to the right of 2, it would be a parabola. Now, this one I do know something about it. What do I know about this parabola? It has to open up, because the number in front of x squared is 1. So I have some other parabola that maybe looks like this. Now, it's a solid dot here, right? Because of the equal sign on the inequality. The way I have that drawn right now, is this a continuous function? Not everywhere, right? Because I have a jump discontinuity. But see, I can change the value of c. If I change the c here on the first part, won't that change the narrowness of the graph? It will start adjusting this. But as I change that c, this c is also affected. And that's going to change where this one is. So what we're trying to do is find the perfect c that's going to bring those two pieces together. Do you all see that? You understand? That seems like a pretty big challenge, though, to be able to find that c. So all we have to do is go and think about what it is we need the graph to do. What is it that we need? I need the limit from the left, right, to equal what? The limit from the right, right? If these two limits come together at the same place, then I've created that, I've bridged that gap, haven't I? I need my left limit and my right limit to be the same thing. Understand? So let's write that down. I need the limit as x approaches 2 from the left of the function to be equal to, now, what does it need to be equal to? You want to do this? Do you agree that that must be true? Yes? Those limits have to go to the same place. All right, now let's be careful. What is the limit as x approaches 2 from the left of this function? So as I'm approaching 2 from the left, which part am I on? The top one, which is we'll call the blue one, or am I on the black one here? If I'm approaching 2 from the left, I'm on the blue one, right? I'm on the blue one. So what would happen if I go in here and I say, hey, let's let x approach 2? What would you get? Replace it. We're doing like a direct substitution, right? Replace x with 2. It would become what? 2 squared, so 4c plus 6, right? So I'm doing this. I'm going c times 2 squared plus 3 times 2. And also notice I'm working this side down, and I'm going to work both sides of the equation down. That's the way we work these problems. So I need this to be equal to what? What's the limit as x approaches 2 from the right? This time we're on the black one, right? So now I'm coming in here, and I'm replacing my x with 2, and what do I get? 4 plus 2c, or I'll say 2 squared plus c times 2. And that's it. We should be able to solve this equation for c. What do we have? 4c plus 6 must equal 4 plus 2c. Solve that for c. What do we have? 2c equals negative 2. So move your c's to one side, move your 6 to the other side, becomes negative 2. So c is negative 1. Does that make sense, what we've done? So we need our final answer. We've got c, but let's write the function down. Our new the function that should be continuous everywhere should be c times x squared, so negative x squared plus 3x, and then x squared what? Plus cx, but c was negative 1, right? Do y'all see all I did was grab this and replace my c with negative 1 here? Replace c with negative 1, and that's this, right? This is if x was less than 2. This was if x was greater than or equal to 2. Questions, comments, concerns, gripes? How do I know if I got it right? Well, I could check the limit, but how about this? Let me go to that good old-fashioned wind plot program I had shown you. I'm going to have... This should open up. I didn't know if it did, because I didn't know what C was going to be. If C would have turned out positive, it would have opened. I got lucky here when I drew it, because it could. I didn't know what the answer was before I started this, so I got lucky that it actually is opening down. But it could have opened up. What I didn't know is I didn't know if they came together or not. I had to find the C that brought them together. Does that make sense? I'll show you something cooler than that instead of using wind plot. Okay, let me see if y'all can be patient for a minute. I'll show you how to how I would write a code for this. So I'm going to show a couple of plots. The plot, this isn't very big. I'm going to show the plot of c times x squared, what was it, plus 3x? Okay, I'm going to show that on the interval x is from -10 to 10. And then I'm going to show the plot of, the other one was x squared plus c times x, right? And I'm going to show that on x is from -10 to 10. But right now, the computer doesn't know what c is, right? Doesn't know what c is. Manipulate is a command that I can do to allow me to control what c is. So I'm going to control c. I'm going to say from -10 to 10. I don't like that plot range. One more thing. Plot range 20. I don't know how good this is going to be. Okay, here we go. We had two parabolas, all right? Here's a parabola. Sorry, there's one more thing I need to do. I wanted to break it at 2, right? So I'm only going to do the first one between -10 and 2, and the other one from 2 on. Never works out the way I want. Yeah, it was off the graph though. Like it was off my. There we go. That's a little better. Okay. So I had two parabolas, right? One like this, one like this. And this is my control of the c value. All right, so I'm going to control c, and watch how these graphs move. As I control c, see how they're moving? See that? And we were trying to figure out the c that worked, that brought them together to make them continuous. Does that make sense? And we found that it was -1, right? Does that look like it worked? Does it look like that's what made it continuous? Now I could just type -1 in here, and we could probably be pretty convinced that that was the solution. Right? But do you see we have parabola coming in like this, and then we have another parabola, but now it's continuous. I draw it without picking up my pencil. Does that help a little bit, at least with the visualization of what we were doing? Okay. All right. Test on Wednesday. See y'all then? No, y'all want to review, right? A little bit? Okay. All right, let's talk about this review. Questions on the review? 7A. Wait a minute, we just did one like that. Look, this one right here is the exact same problem. Look, right? In fact, I remember this test now. I remember this test. I gave this test, when was it, summer? This past summer. I believe almost every single problem in this test was taken directly out of the homework. And you wouldn't believe the averages on this. It was terrible. And I was very disappointed because I told them, study your homework, do your homework, and I gave them exactly homework problems, but I changed the letters. Like, this is exactly that problem, but T's instead of X's. Some of them are exactly the same. Yeah. And people, there's no excuse for that. There's absolutely no excuse. If the idea is that you study the homework, you understand the homework. Now, I understand things happen during a test, and you get the anxiety, but at the end of it all, I mean, like, if I give you the exact problem that I told you to study. Okay, so are we good with that one at least? Okay. 4B. Oh, this is a great problem. And the reason why you should be asking about a problem like this is because I really didn't do one like this, but I believe this was one of your homework problems. It was? All of them were then, okay. I haven't done this in calculus, but I've done it in like college algebra before. I've given students a review. You know, do these problems, college algebra, do these problems, get ready for the test. And then they come in the test, I give them the review as the test. And I've had like complete bombs of it. And I just don't get that. But I think there's a big thing to be said about anxiety, test anxiety, right? I mean, you can feel real good and then you come in and it's just like, it all goes away. So you got to work on that. Anybody going to grad school, thinking you might want to go to grad school one day? Usually the further you get on with academics, the fewer tests and the more they're worth. So like a lot of times, like after you get to like junior, senior level graduate school, it's usually like 2 tests. Midterm, final, that's it, 50-50, that's it. So you've got to perform on the test. There's no other way about it. So we want to kind of work on that anxiety part of it. What's the best way to prepare for a test? Study, but yeah, that's too vague. You sit down with a set of problems. You put yourself in the testing environment. You say, okay, do I have an hour, 40 minutes right now? No distractions. Sit down. Can't use anything except this, your calculator, right? And actually try and simulate the test. And when you get stuck, move on to another problem. You can't go and look it up. If you start simulating that at home, it'll help you. The question is, what do you use to study to give yourself that practice test? Well, you go do this, right? And then after you finish these, you go find another problem in the book right next to this one that looked like it, and you try that one. You make a new test for yourself, and you try that. Yeah. Yeah, let's talk about it at the end. You will, but let's get to this. All right, this is a tough problem. Okay, as x goes to 0, what does the top go to? Sine of 0 is 0. Okay, bottom left, 0 plus tangent of 0 is 0. So you kind of got to know what all those are before you can do this. And that gives you 0 over 0, which is something we're going to have to do, work with. There's nothing really natural in this problem. And I think you could probably work on it for days and days and not see it. So let me show you the approach. And you kind of tell me why I'm doing this. So I decided to multiply top and bottom by 1 over x. Why would I be using that sort of approach to this? That's right. If x is going to go to 0, then this right here is going to become sine x over x, isn't it? And sine x over x approaches 1 when x approaches 0, right? That was one of the ones that I wanted everyone to know. We had a quiz on it. That's 1. But just because it's 1 there, let's not get confused. What is this one? 0. Because of the difference of where x is going, right? This one is 1 because I said it was. And then, well, actually, I think I showed you squeeze theorem was how we get that. But this one was bounded over infinity, and that went to 0. So just be careful where you're headed before you start using these things. Okay, so yes, you see that sine x over x up here is going to give me 1. And then what about down here? I'm going to have 1, and then when I distribute this, tan x over x, we never talked about what tan x over x does. So we'll have to maybe look at that. Let's just kind of distribute through and see what happens. I'm not taking my limit yet. I'm going to circle in blue the things that I'm happy with. right? I'm happy with those two. This one's going to go to 1. This one's going to go to 1, so I'm not worried about it. This is the only one I still need to resolve. So what I'll do is on the side here, let me just take a look at that. What is the limit as x goes to 0 of tan x over x? Any ideas on what I can do with that? Separate how? Okay, limit x goes to 0, tan x over 1, and then 1 over x. I did tell you all to do that, right? Anytime you run into a little issue with these, just try and peel them apart. What now? Anything else? I tell you what to do when you get stuck like that? Rewrite tan as sine over cosine. So take things in terms of sine and cosine. And I'll even go further. Can I go sine x over 1 times 1 over cosine x times 1 over x? Is that all right? Do you see it? What is it? What do you see there? Yeah, isn't this, can I slide those together? That's just sine x over x, right? And then on the side I got 1 over cosine? What is sine x over x going to be? That's going to be 1. Times 1 over cosine x. So this is going to, this right here is going to go to, I'm going to take the limit now, okay? So I'm taking the limit, so I'm not writing it again. It's 1 times, what's cosine of 0? 1, so 1 over 1, so it's 1. So that goes, 1 times 1 is 0. 1 times 1 is 1. So back up to this now, I know what this is going to go to, right? Up here. This right here. That tan x over x is going to be 1. So my answer up here is 1 over 1 plus 1, which is 1/2. One of the realities, I guess, that we run into in calculus is that even if I show you a bunch of problems, every problem is unique in the sense that you have to understand the concept. It can't just be like, it's like in college algebra, you were given the quadratic formula, right? And then if anyone gave you a quadratic, you just applied the formula. Apply the formula. In calculus, the limit idea is so vague that when I give you 100 limits, the 101st limit I give you could be completely different than the previous 100. As long as you understand the ideas and the way things are behaving, you have that chance. But if you're just looking for, okay, it's got to look exactly like that, and then I know what to do with it, it's going to be a challenge. What else? This is available through email, right? I sent it through. The reason I didn't post it online is because I needed to tell you only to do first 7 and to not worry about number 5. If I just would have like posted it, people would have been like, "Oh my God, have you seen like number 13? I don't know what the hell. I'm gonna go drop the class." Like you would have not known what to do. So that's why I emailed it. So check your email if you haven't. What else? You want to talk about things that might be on tests that aren't on this, or we can do that after in a minute, or you want to keep going through this? Well, off of this, it's only the first 7. But it's not limited to just this. Like, here's something I thought about. I was walking into work today, and I was thinking about a problem that I might give you on the test. And this is what came to my mind. I don't know why I was thinking about this walking in the test. I was curious how you would handle this. Let's say that you have, well, I'll make it straight. Whoa, that's not working. Let's say you have a perfectly straight, we're looking from the top. This is a river. Okay? Well, let me draw it first, and then I'll tell you what I want. And then what I have is I want to build next to this river. Remember, we're looking from the top. I want to build this rectangular pen next to the river. I'm going to put, like, I don't know, some sort of animal that's afraid of the water that'll just go drink but won't go across the river or it'll die. So this pen should be enough just to build this side and this side and this side. Should be enough to keep these animals contained, all right? Okay? But I'm going to have a couple animals and they don't always get along, so I'm going to want to be able to build 3 identical pens. Those don't look identical. Those are 3 identical pens, and I'll put my little animals in each one, right? You okay with that? I have 1,200 feet of fence. Find a formula for the area of, well, I should say total area in terms of X. So I forgot to label one thing on this. From here to here, we want to call X. So that's what I was thinking about on my way in. And I was like, I wonder if I just like threw that at the class on the test, how would they handle that? Would it be, you know, asshole, he never gave us anything like this? Or would it be more like, well, hold on, you know, I've found formulas before for different things and solved, so maybe I can start to put this together, you know? So let's see if we can, as a class, come up with what it is that I'm looking for here. Length times width is what? Okay, so area, so would you all agree that the area of the total enclosure, that's what I'm trying to find the formula for. The area of the entire enclosure is this, right? Everything in there. Yes? Okay, that's the area. So the area here that I'm looking for, I've been told, is length times width. Now, right now, have I done what's asked? Have I found a formula for the area in terms of X? No, my area depends on L and W don't appear in this picture. I just need my area to have X in it and X only, and that's it, and I'm done. I'm trying to find an area function, basically. So if this is X, right, then this side over here, the whole length, we can call it something else. Why? Because we need to. No. Who said that? I know. So you want to call it Y? Now, I've also heard we can call this 3X. Can we call this 3X? If they're square. I said they're identical, but I didn't say that they're identical squares. So identical meaning whatever this is, this one's the same dimension, this one's the same dimension. So you could have like this. I'll draw a miniature version over here. You could have the river over here, and you could have this crazy-ass looking thing like this, where you got some really, really narrow animals in there, right? They look square, correct, but I did not say they were, so you cannot assume they are. But that's a good thing. To think 3X is good, but I almost drew them intentionally square so that it would force people to think square, but I did not say it's square. So you can't assume it. So, but is this okay to write it this way? XY. So what is your area now in terms of your picture? I'm just going to use A instead of area. A is XY. So have we gotten any closer? Well, we've got X in there, but it needs to be in terms of X only, just X. So you can't have Y in there. What's that? That would be X's, you're solving for X there. We don't want to solve for X. We want A equals, and then the only thing on the right side has X's. There's nothing but X's on the right side. Is there anything that seems somewhat unsettling so far in the problem? Or not unsettling, but you feel like you haven't used the 1,200 feet. I mean, that should be like in your head, like, wait a minute, hold on. He didn't just give me 1,200 feet just for fun, right? You only have 1,200 feet of fence, right? So can Y be 1,000 feet long? It can be 1,000 if the rest of it used for this, right? But there's some restrictions. Y cannot be 2,000, right? X can't be something. So that 1,200 somehow tells us something here. So what is it? This is like a perimeter almost, right? It's your total length of fence. So in a separate little thought over here, tell me about the 1,200. Wait, hold on. The what? This is fence. Everything in black is fence. Fence, 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 and fence. But you don't need fence along the river. Okay, what's equal to 1,200 is the total fence you're going to have, right? That would be this right here, right? Plus this right here, plus this right here, plus this right here. So how many? Okay, 4 X's, right? Plus the whole back side here, which we said was Y, right? Do you agree that that would be using up all the fence? I take the 4 X's plus the Y, and that's equal to 1,200. What's the value of that? Why? How does that help? Exactly. If I take this equation and solve it for Y, I can plug that back in here, and then everything will be in terms of X. You see that? So solve this for Y, and you get Y is what? 1,200 minus 4X. You divide it. Be careful. Right? 1,200 minus 4X is Y. Now come back up to your area. Your area is X times what? 1,200 minus 4X. Is your area now in terms of X? You're done. So would you have been upset about that? You would have been pretty upset about that. But now that I've shown it to you, does it seem reasonable?
Is it going to be similar to that?
Well, see, it depends on what we think, what we classify as similar, you know? I like these fence problems, and here's why. What we're going to do later on in this class is I'm going to say, all right, forget all this. I'm going to say you have 1,200 feet of fence. You want to build it like this, right? Exactly what are the dimensions that would give me the maximum area? The most area possible. Now, you may agree or disagree with this. I don't know if I'll be able to convince you right now, but one way I could build that thing would be really, really, really narrow, right? Like this. Really long, and then make my pins like this. I could do that. Those poor animals, right? And that would have a certain, yeah, that are afraid of water. It's punishment. So that would have a certain area to it, wouldn't it? That would have a certain area. And then maybe I could do this. That seems more reasonable, right? Something like that. I don't know how many I had, but that's a good question. Would it always be the same? Or I could do something like this. like I had said, very narrow, right? Question is, if I'm using 1,200 feet of fence, if I use all 1,200 feet, are all three of these scenarios exactly the same area? Let's try something more simple. Let's say I have 4 feet of fence. 4 feet, okay? 4 feet. And I want to build a rectangle. And give a couple of different. I only have 4 feet of fence. Here's one way I could do it, right? 1, 1, 1, 1. That'd be a square, right? Okay, here's another way I could do it. 4 feet might be hard, but I could do like 2, 2, half, half. That's 5. Well, I was just listening to what I was being told. Could I use 2, 2? I only have 4 feet of fence. 1.5, 1.5, and 0.5, 0.5, something like that. Right? These pictures don't look right, but what is something else I could do? 0.25? I mean, there's all sorts of different combinations, but let's just look at these two cases right here. What's the area of this? Length times width, 1. What's the area of this? 0.75 or something like that. They're not the same. What I'm trying to convince you of is that if you have a fixed perimeter, the different ways you construct it, you have different areas. And so the question would be, which way do I build it so I get the most area? And that's exactly what the question is that we're asking here. Well, not today. We're not asking this question. Right now, I'm just saying, hey, come up with the function. But later on, we're actually going to do calculus on that function to figure out when it's the largest it can possibly be. This might be another way I can convince you that this area is going to vary. Right now, the way this function is written over here, the area depends on what? X. And X is how long this side is, right? Okay, what is this? If I were to graph this, area function, area X, what type of graph is this? Distribute your X through, right? And you get a parabola. Which way does it open? Down, because you have a negative in front of what would be the X squared term. So it opens down, so it would look like this. Isn't there a highest point on a parabola? And that would be where you get your maximum area. So you can see from just this graph of that parabola that there is some value of X which gives me the highest possible or maximum area. So this is where we're headed because calculus is useful. We use it for something. This is what we use it for. If I'm building something, right, I want to get the most out of it. Right? I don't want to waste space. And you can also do it in, another way. You can say, I want these pens to have a certain area. Build it so you use the least amount of fence. That's very useful. One of the classic examples is, and we'll do this in this class also, is if I want to build a container to hold 12 ounces of whatever, right? Coke, non-alcoholic beer, or beer. No matter what it is, if I want to build a can, what should the dimensions of that can be so that I hold 12 ounces, but I use the least amount of surface area, least amount of aluminum? Right? If I'm a manufacturer, I want to build a can so I'm using the least amount of aluminum because aluminum costs me money, right? So the dimensions of this can are going to be dictated by us being able to solve a problem of figuring out when something is the lowest, and we'll use calculus for that. So we'll determine later on that the dimensions of a can are not random. It's what they use in order to not waste money, waste aluminum. These are called optimization problems, and you'll enjoy them later. We have a lot to do before we can get to those, though. All right, I'm going off subject here. What else? What else did we talk about that wasn't on this review? Was there any difference quotient on here? There wasn't, but you had to do some limits where you had to simplify things, right? Where you had to do like conjugate, things like that. Okay. Can you draw me a function if I give you conditions, like on number 2? All right with that? Give you some conditions of a function. You want me to do one? I'll just do this one or do this one? Okay. So I give you a condition, limit x approaches 0 from the left of f of x must be infinity. That's condition A. Condition B, limit x approaches 0 from the right of f of x must also be infinity. C, I give you that f of 0 must be 1. D, the limit x approaches 2 from the, is that 2? Yeah, 2. F of x must be negative 1. E, limit x approaches 2 from the right of the function must be 2. And finally, condition F is that f of 2 is undefined. So what does it mean that as I approach 0 from the left, I have to be infinite? As I'm moving towards 0 from the left, my graph is going to head towards positive infinity, which means I have like a vertical asymptote there. So I know that it has to do something like this. Does that make sense? And then as I move towards 0 from the right, it has to do the same thing, right? So it looks something like this. But then I say f of 0 is 1. So my function is actually defined at 0, isn't it? I have a value of 1. So that means I'll go to 0. I'll go, let's say, up 1 right here, and I'll put a dot. See how that satisfies all the conditions? From the left, approaching 0 from the left, it goes to infinity. From the right, it goes to infinity. At 0, it is 1. So conditions A, B, and C are all being met there. How about condition D? I approach 2 from the left. Where am I headed? Negative 1. So here's negative 1. I'm approaching 2. So let's say 2 is out here. As I head towards 2, I need to be headed towards negative 1. So how about this? Does that look like it works? So I head towards 2, x value of 2 from the left. I'm headed towards negative 1. What if I'm approaching 2 from the right? I need to be headed up to 2. So let's say that 2 is up here. Me coming in like this. From the right, I'm approaching a value of 2 up here. And then f of 2 being undefined means I should not fill in one of these, right? I just leave them as open holes here. And then to finish the graph off, let's just connect things. Let's make it a function. And it doesn't really matter how you draw the rest of the pieces, as long as it still satisfies the conditions. So that's one variation of an answer. So everyone should have different looking graphs on these, but they should all at least satisfy these conditions. So you need to connect them. Don't just leave them with gaps between them, because we want the function to be defined. If I draw a line through 2, I should not hit any part of my graph. It should have no definition for my function there. Okay? Anything else? Undefined is when we're talking about a specific point on the graph. Undefined. So at 2, if I say, hey, go to 2 and tell me what the function's value is, you look up and down, you're like, hey, wait, there are no dots. There's nothing here, right? Does not exist is when we are looking at the limit. So does not exist only talks about limits, so it's what you're approaching. Okay? By the way, what would the limit as x approaches 2 of this function be? That would be does not exist, right? Because from the left it's down here, from the right it's up here. What would the limit as x approaches 0 of this function be? Infinity. Because from the left it's headed to infinity, and from the right it's headed to infinity. They're headed to the same place, infinity. Trying to see if I had anything else. Yes? Oh, yeah. You want to go over something like that? Yeah. Very, very possible that would be there. In fact, now that you mention it, I think I'll put it on there. I'm kidding. All right. So this problem, I haven't put what the questions would be yet, but what I've done is I've given you the function, and the first thing you need to do is to graph it, to draw a picture. All right. So let me help draw this out. I'll help you draw this. Probably don't need it to be that big, but see what happens. So how many pieces do we have for this function? 3, right? Our lines of separation are like at 0, and then let's say 2. I'll count. Say that's 1. No. Let's say 1, 2, 3, 4. So if we could imagine like 3 imaginary regions, right, separated by these 2 lines. Everyone understand where those lines come from? Our breaks are at 0. To the left of 0, we're up here. Between 0 and 2, we're this, and then after 2, we're this. Yeah? So I need to draw these on each piece. So what does x minus 1 look like when you're less than 0? So anyone know what x minus 1 looks like? X minus 1 is a line, right? It's like y equals mx plus b. What's the slope of this line? 1. What's its y-intercept? -1. So here's -1. Here's -2. -3. So if I'm going to draw this line, I have a y-intercept of -1 and a slope of 1, which means it should go up 1 over 1, up 1 over 1, right? But I can't go to the right. I have to go to the left. Why do I go to the left? Because it's only for x less than 0. Are there any questions on that? I mean, if you wanted to, you could draw it up to the right, but you need to erase it later. Like connect everything together and then erase it out because you only want it to do this. Now I have, what is going on right here? Is that solid or is it open? It's open because it's not equal, right? So any questions on that? That's your first piece. Second piece, I need to be a parabola, right? Which opens which way? Down between 0 and 2. So what would be happening at 0 here? Where would I be? I'd be at 4, wouldn't I? So let's say this is 1, 2, 3, say 4. There's 4 up there. And I would be a solid dot, or would I be an open circle there? Solid, because it's defined there. So I'm going to put this solid dot here. And then what would the value be getting close to as I got close to 2 here? If I plug 2 in, what would it be? 0. So I should be down here, but I'm going to put an open hole there. And then I'm going to make the parabola open down like that. Does that make sense? Line, parabola that opens down. Then you have this. What's this? 3x minus 6 is a line, right? Slope is 3, y-intercept is -6. Now I could do that, right? Come way down here and graph a line and stuff. But tell me, what would the value be at 2? It'd be 0, wouldn't it? So I'll draw this one in blue. So at 2, we should be at 0, so I fill in a solid dot there, don't I? See that solid dot come in here? And then to the right, it should just be slope 3. So up 3 over 1, up 3 over 1. So I'm just going to draw kind of steep like this. I'm not being exact. If you wanted to, that's 3 there. It's up 3 over 1. Do y'all agree? Okay, so what are the things that you think I might ask you? Okay, what's the limit? X approaches 0 from the left. X approaches 0 from the right. X approaches 0. What's f of 0? Now, I'm not writing limit over and over and over because of time. So what is the limit as x approaches 0 from the left? Where are we headed? We're headed to -1, right? So this would be -1. What's the limit as x approaches 0 from the right? Up to 4. What's the limit as x approaches 0? I don't specify the sides. You have to check both sides. They're not the same, so it does not exist. What's f of 0? 4, because we had a solid dot up here, right? Then I could say something like all of these questions again, but x approaching what? 2, 2, 2, 2. So what would the limit from the left, as x approaches 2 from the left, what's the answer? 0 from the right? 0. Then what's the limit without telling you left or right? 0. What's f of 2? 0. So all of them would have been 0. Make sense? So on the test, if I give you something like that, I'll keep the graphs like pretty simple, meaning linear, quadratic at the most, and then maybe sine, cosine. That's about it. I'm not going to give you some crazy stuff you haven't seen. Am I what? Yeah, it would be like the one I did earlier today. But see, on that one that we did earlier, we didn't have, to do this problem, you actually don't have to draw the function. You just have to find, this is all the work that you would have had to have done. I only drew the function to help you see what it was that we were actually doing. Well, we only have about 6 minutes, so I'm not quite sure what kind of value we could get out of another problem. Let's talk about what you can have for the test. Your formula sheets that are online, you'll know what I'm talking about? Let me take a look at this real quick. We had a very heated debate, the math department again, on Friday about what students should be allowed to use and not use on tests. I think reference page 1 is fair game because it's all algebra, geometry stuff. That's okay to have that. So you can have reference page 2. I don't think you really need that or that. Yeah, and all that's, we haven't even gotten there. So all you need is reference page 1 and 2. So you can have that, okay? You can have reference page 1 and 2. Don't bring the whole stack, just reference page 1 and 2. They can be on separate paper, that's okay. And then in addition to that, I'm going to allow you to have one 8.5 by 11 sheet. You can write down any sort of steps or procedures on things, like if you want to write a summary of limits, like what happens if I get fixed over 0, or if you want to write a summary of that, you can. What you cannot have are worked out problems. All right, you can't just take the review and a bunch of homework problems, throw them on a piece of paper. That's not allowed. All right. Limit x goes to 0 of sine x over x equals 1 can be on there because that was a formula I gave you. That would be okay, but you couldn't just take. Yeah, well, that's on the reference page, but if you wanted to draw your own, you could. Yeah, well, wait, no, the unit circle is not on here. It's just this, yeah. So if you want to draw a unit circle or you don't have to draw, you can copy and paste it. It's okay. What I was saying, though, is like, you couldn't just like put this problem down on your sheet. Steps and procedures, things that help you without giving you an unfair advantage. I will check those when I give you the test. I'll walk around and I'll check them. All right? I have no idea. I haven't written the test. Yeah. I have no idea. Let's see. I mean, this one was, let's see, 1, 2, 3, 4. See, but these have multiple parts. 5, 6. I don't want to lock myself into anything. I'll say, how about in between 1 and infinity? No, it'll be probably under 15. Yeah, but see, some of them are part A and B, so I don't know. I mean, pardon? Tonight, I just finish up all your homework. Yeah, I mean, study, get together. Is anyone going to get together in a group and study or anything? No? Did I